Yes, that's it. I've never been there. I will never go there. I will put a link to it.
Yeah. It's actually
So I've heard. I'm not falling for it.
I mean, it's gross. It's not falling for All right, it is 7 o'clock, so I'm getting started. I found out what the problem was, with this make file. It was cyclic. Okay, in other words, in order to generate an include file, I was relying on an executable that relies on the include file. So it was a cyclic dependency. It was my fault. I fixed it. Okay. So here's the new make file that works. Okay. So I'm going to explain the make file a little bit, and then I'll explain the solution to the Factorial program. I know most of you, got it done, way before, the date, the due date, the deadline. But I'm going to share my solution with you, and I'll kind of explain it along the way too. Because there were some questions that was brought to me about, okay, should I have this instruction here, or should I use this addressing mode here? Some of those really does not matter as far as this class is concerned, but that's only because of the way we use Linux and also the stack. Okay, but it's in general, it's not. Some of those are not exactly good ideas. So I'm going to explain, some of those things in today's class, and also why we have to do things in a certain way. But before we go any further, I just want to explain how this works. It's all fixed. It is now working. It's because I was lazy and I did not want to set up a separate executable to generate the include file. So let me adjust the monitor. It's still displaying stuff off the screen on that side. So I can probably change the zoom or have someone to change the zoom, because I think it has to do with the zooming of this one here. Okay, so
Recording?
It is recording. Yep.
Audio working this time?
Double checking. Yes, it is. Good to double check. Yes. Okay, so this is working now. I separate the executable. There are two executables. One executable is the actual product. This is the program that I want this makefile to create. This is the final product. The other executable, it has a different name. This executable, the only purpose of this executable is to generate the header file required by the assembly file. Okay, so I separate the two executables into two different names. Now that I separate it into two different names, I have two different rules for these executables. So one is used here. Okay, this is basically the executable to generate the include file. It is the dependency of the include file itself, and this is how I generate the include file, by running the include file generator, which is this file here. And once I separate those into two, everything is working. So I'm going to show you guys exactly how this works. So I will make clean first, which delete all the files that are not relevant, and I just say make. Okay. Make again. Darn it! It was working before.
Did you save it?
Yeah, it was saved. I was using exactly the same file system. It was working before. Okay, let me see if I can do this. Let me see if I can just make that include file. New. Fatal error. It still needs to, okay, there's still some sort of dependency that is not resolved, so I'm going to have to, look into this one and get it fixed. Okay, so close, so close. Okay, so the next thing I want to do is to show you the solution to the Factorial program. So first of all, I'm just curious. I just want to find out how many people turned it in. So we want to look at Factorial, which is here. Okay, 49 out of about 55 students or so. That's not bad. I mean, that's like, almost 90% of students turning in. Okay, so I'm gonna give you the solution anyway. I know most of you do not really need it, but I'm gonna disclose this solution. Okay, down with the file. All right, so here's the Factorial folder. Okay, are there any questions that I can answer?
No.
Are there any questions that I can answer? Okay, apparently not. All right. So what we'll do is I'm just going to take a look at the Factorial program here, and I'll give you the answer to that, to this particular homework assignment. I know most of you, turned it in already and you know how to do it, but I still want to kind of go over the process because I want to point out potential problems with the implementations. Okay, so here we go. So I start with the usual stuff. EBP, old EBP equal to 0. Return address equals to old EBP plus 4. And then the parameter, which is n, is 4 bytes on top of the return address. Now, even though I do this every single time, and you see this and go like, oh, okay, I kind of know this stuff, you still want to make sure that you understand why these labels are defined as such. Okay? What are they really representing? How does it relate to the stuff that is on the stack when the subroutine is called? And so you kind of have to remind yourself, why you have these constants and why they are defined like this. Okay? And then when we work on the actual, subroutine, I know most of you, know the usual, entry code and the exit code already, which is push EBP to save the EBP from the caller of this subroutine. And then we modify it by taking a snapshot of the stack pointer so that the frame pointer becomes, it points to a certain point that is important to me as a subroutine, in this case, Factorial. And then the exit code is the reverse of this. I'm undoing, all the changes by a single instruction of moving EBP back into ESP. And then I can do a pop L EBP here and then do a return. And then at this point, I have my frame pointer set up, and I can start to use n as a displacement to find the parameter itself. Now, when you look at the C code, the first thing we need to do is to compare n to 0 and see whether we should, go for the recursion or just return a value of 1. Okay, that part is relatively easy. It is just a compare instruction with 0, and we want to use, n % EBP, to do that part. The C code is using signed integers, and that was kind of an oversight on my part. But in your implementation, you should be doing exactly the same thing as what the C code is doing. Yep.
For the compare L, isn't what's passed into the parameter is also lands in EAX, right?
I'm not sure whether that is always going to be EAX.
But is it? It's not.
Did you read about the convention?
Like when I did a print EAX after I ran at that breakpoint, it would show that it was whatever I put in as the parameter for my Factorial.
I think the GCC compiler does have a convention like that, but only for the first parameter.
Right.
Only for the first parameter, it is also put into EAX. So if you rely on that, that's okay with me. It's not a problem. But you still need to retrieve parameter n from the stack later on, or you have to push it or save it into some other register at some point. Okay, so it's not gonna save you from having to access it through the stack altogether. I don't think.
Okay.
Okay, so
what if I used instead of n? What if I used 8? Because that's instead of n.
That's fine,
Okay.
because you can, yeah. The way I define it is just so that everything is symbolic, and I don't have to think about the offset.
Right.
Because later on, okay, for homework assignments like this, you don't have to deal with the problem that I usually have to deal with. Okay, because I have to maintain programs for years. Okay, 10 years is not uncommon for programs that I have to maintain and be able to read the program and fix certain things or add additional features. So if I use constants like an offset of 8 from where EBB points to, 3 weeks later, I look back at the code and I would have a question of what is an 8, a displacement of 8 from where EBB points to. But if I use the name of the parameter, especially when I have the C code also included, I know what that really means. I know what n is. What n means. It is a displacement from where EBB points to parameter n itself. So to me, it is useful because I need to maintain my programs for a long period of time. Whereas for you get it done, you turn it in, you get the points, and you're happy, right? So, but the same thing applies to when you actually go out to work and you have to work on programs that you need to maintain over a longer period of time. Using constant offsets, is really hard to maintain.
And other people probably have more difficulty reading it too.
Right, and then somebody's going to change the program to use symbolic constants. Just so that it is easier to read. But it's okay for this homework assignment to use just a regular 8 instead of n defined this way. Okay, so after the comparison, I would do a conditional branch. A JZ is going to be okay, even though it's not really the best way to do it, because in the original question, it is whether it's greater than or not. So if I want to be truthful to the original C code, I'm going to have to say if it is not greater than. So if n is not greater than, I need to go to the else case. So I'm going to define an else label, E-L-S-E label over here. Okay. Now, if I do not perform the conditional branch,
J and A should work as well.
say again?
J and A should work as well.
Not exactly, because the original code in C, says that n is a signed number. So if it is a signed number, if I give you a negative value, then it should still go to the else branch. If you use a JZ in this case or JNA in this case, then it will not branch correctly because it is looking at the number as a unsigned number. So I'm doing this assignment, the 100% consistent way, at least with the original C code. Okay, because I want to kind of emphasize, if you want to be consistent with the original C code in terms of the use of signed numbers versus unsigned, this is the way we have to do it.
But it's not correct, yeah? You can't say a factorial for -1 is 1.
You cannot,
Yeah, so
right?
it's not
But if you want to be consistent with the C code, then in the C code, because it is expecting a signed integer, you can still pass a negative value to the C code. Because this is not a math class, so I'm not going to argue whether there is a factorial of a negative integer.
To be consistent or to be correct?
Say again?
What is better, to be consistent or be correct?
To be consistent with the C code, that is what we're striving for is the consistency with the C code. Okay, so if I want to be 100% consistent, I would use JNG in this case. If n is not greater than 0, then I go to the else case. The else case is the easy one because all we have to do is to put a 1 into EAX. Okay, can I answer any questions back there? Any questions for me? No? Okay. Because if I can hear you, so can students in front of you, and that would be kind of distracting. All right. So in this case, I have else going to here, and just putting a 1 into EAX is the same thing as returning a value of 1. So that part is done. If I do not perform the branch, that means I have to perform this calculation here. The multiplication comes last. This is kind of a confusion because of the way we use infix notation. Now when we use infix notation, we have the concept of, oh, we know what n is, we can now do the multiplication, and then we call factorial to finish the operation. But that is not the case because if you think about it, multiplication takes 2 numbers, right? So when I only have n, what am I multiplying n with? There's nothing to multiply it with. So I have to have n and the result of the factorial of n minus 1 before we can perform the multiplication operation. So that is why we should call factorial first before we do the multiplication. Because somebody asked me, I think this question was, why do we have to call factorial before the multiplication instruction? This is why. The confusion, stems from our use of infix notation, as I said a little bit earlier. Because in the infix notation, it says, n times factorial of something. So if you read it in that order from left to right, it seems to imply that we can get n, we do the multiplication, and then we can call factorial. But that really is not the order of doing things. We have to get n, we have to get the factorial of n minus 1, and then we can perform the multiplication. Okay. Any questions I can answer? No? Okay. So now we are going to do exactly that. So the next question is, how do we call factorial with a parameter of n minus 1? There are many ways to do this. Okay. There's one way where you can put n into a register, decrease that register by 1, and then push that register on the stack. That's that way. You can push n on the stack first, and then decrease whatever you just pushed on the stack by 1. That's the other way to do it. Okay? These are not the only two ways to do it, but these are the two ways that are most common when we have a application like this. So personally, I like this approach the most because it does not require the use of an intermediate register. So I don't have to use a particular register to do the calculation and then push that register on the stack. So I can do a subtract 1 here from whatever the stack pointer is pointing to. So this is the same thing as pushing n minus 1 on the stack. Are there any questions about these two instructions?
And that's supposed to be a positive 1 or
For your subtraction.
Oh, you're right. Okay, I'm subtracting 1 and not subtracting negative 1. Thank you. Or I can change it to add L, but not both. Double negation is not good. Okay. So this will do it. It was just subtract 1 from whatever I just push on the stack, and I just push the value of parameter n on the stack. So this is one way to accomplish pushing n minus 1 on the stack.
You can also do this by not using ESP by saying -4 EBP, right?
No, it's not the same thing. I'm not changing parameter n itself. I'm changing a copy of n.
No, -4 from EBP. You can move down from EBP. We'll reach that.
Oh,
Yeah.
okay. Let me see what you're talking about here. Are you talking about this?
Yeah.
But that is okay. Now this is worth its own discussion. Okay, whenever you specify a negative displacement relative to the stack pointer, you have to be extremely careful, because what the stack pointer is pointing to, okay, the stack pointer divides the stack or the memory space allocated to the stack into two portions. Okay, so let's say this is the last byte, or this is the byte that the stack pointer points to. It divides the stack into two portions. One portion is whatever is in use, and the other portion is whatever is available to the system. Okay? In other words, whatever is below what ESP points to is available to ISRs, interrupt surface routines, and other things to use. So that's why if you use that addressing mode and you specify a negative displacement to whatever the stack pointer points to, it is extremely dangerous.
No, not ESP, but EBP.
The EBP?
Yeah. It's the same thing, right?
It is the same thing in this case, but why use something that is relative to EBP when ESP is pointing to that very same thing that you need to access? The reason why it's not a good idea to use EBP is like this. Okay, so you're talking about this, right? Yes, at this point it is pointing to the same thing, but what if for some reason that you have another push operation here to save a particular register? That will change it, right? Because if I have any additional push and pops ahead of these two instructions, then it is no longer at -4 compared to where EBP points to. But if I use ESP, it still works because it is local to that particular instruction. So in this case, It's better.
It's like the last one. Right?
Yeah, the last one is just basically saying whatever I just push on the stack. So using this instruction or this addressing mode is more appropriate. Even though the other operand would accomplish exactly the same thing in this case, it is much more sensitive to additional pushes that I might need to do later on when I write this program. The use of push and pop is very popular when you find out that, oh, you know what, I need to save this register, I need to save the value of this register, and then later on I make use of it, then you can end up with additional pushes ahead of these two instructions, and that will change the offset to what you just push on the stack if you use EBP as a reference point. But when you use ESP as a reference point, it doesn't change. All right, so now we can call the factorial. So call factorial. When factorial comes back, what I just pushed on the stack, which is n-1, do I have any use of the value n-1 in this subroutine other than setting it up as a parameter to the next invocation? Nope, I don't have any use of n-1. I have use of n itself, but not n-1. So these 4 bytes that the stack pointer is pointing at right now is of no use to me anymore. So I should do this in order to reclaim those 4 bytes on the stack. The question now is, do I have to do it? No, you don't have to. But if you don't do this, and as a programming practice, it is just a waste of space. Okay, it is not a good programming practice not to deallocate space that you are not using anymore. I'm not going to take any points off. Okay, if you forget to reclaim those 4 bytes, which are allocated as the parameter to the next invocation of factorial, I'm not going to take any points off. But it is not a good programming. It's not a good programming practice because you have to deallocate stuff that you're not using anymore. I think that probably accounts for why some programs chew up like gigabytes of memory.
This is local. So
Say again?
this is local. Local.
This
Not
is
global.
bloatware?
Local.
Local?
Local versus global.
Because when you go out of the subroutine, it frees the memory.
Right, exactly. But you don't need. Okay, I'm gonna finish this program, and then later on I come back and remove this instruction. It's still gonna work. It's just it's not a good way of writing your program. Okay, right now I have n and I have the result of factorial. I'm ready to execute the multiply instruction. The question is, how am I going to specify the multiply instruction? Do I have to move things around and do things like that? The answer is no, I have everything in place already. Because I can, what is EAX containing right now at the cursor?
And
Return value of factorial when I gave it n-1 as a parameter. Isn't that one of the things that I need to multiply anyway? And what is EAX to the mul instruction?
It's the default multiplier.
It's the hidden operand, okay? It's the default and hidden operand. So I have one operand already set up. What is the other operand to multiply? Just n, right? So I'm pretty much all set up here. So the only thing left to do is to execute the multiply long instruction and give it n. Now, since I said that I have to be consistent with my discussion here, technically speaking, I have to use the signed version of multiply and not the unsigned version of multiply. Yep.
So would it have been alright if we did use
Yeah,
it's a different operand like EBX?
EBX. Yeah, you can use EBX.
I use EBX.
You have to move it around,
Yeah.
Yeah, but you don't really have to. You can just use this.
This is much better than the way I did it. I was just wondering.
Well, it's not much better. It's just another way that will make it work. Yep.
In the case of this particular program, if you don't do the add-l $sign forward to the ESP, reclaiming memory, then you'll run out of memory space faster. So you'll be able to do less Factorial, right?
Yes. No, it is not true. In this particular program, if you do not have the add L $4 to ESP, it does not use up any more memory than even if you do. The reason is because there's no recursion after this point. So no one is stacking on top of this, and as a result, the memory that quote unquote is wasted is really not, not useful. If you think about how the stack is set up,
Because by the time it gets to this point, all the recursion's already happened. So everything's already been reclaimed. Except for the last piece.
So we have n, return address, OEVP, right? And then what do we have? We have n minus 1, the return address, another EVP, and then we have n minus 2, the return address, and then another EVP here, right? So the space that we are wasting is not being stacked up because it is after the fact. Now, on the other hand, if I have any type of recursion after the call factorial call, then it becomes effective because that space that I could have reclaimed before I call again becomes used up space on the stack that is taking up space but not doing anything useful. It's even worse if this is stuck in a loop, because if this is in a loop, then every iteration of the loop will waste some additional space. And if your loop, if it's a really lengthy iteration, then you end up wasting a lot of space just by running through that loop.
But I have my $L$4 as an ESP. My function giving my thing is kind of like a weird number with a negative and the star and a long number. Then it's all
It should not give you that effect. I mean, it's just not a good programming practice.
Honestly, just put like add-L there, never seems solved out. That's what we're going for.
That usually is because you have some other use of the stack that I'm not using in my program. Yep. All right, so I have the multiply instruction here. Is there anything else I have to do about the multiply instruction? Nope, the multiply instruction stores the result in EAX and EDX. So I'm really all done here. Except for a unconditional branch to the last point, because, otherwise it will go through the else label and move a 1 into EAX. So I do have to make sure that I branch around that to the label else if, and that should do it. This is one implementation of the Factorial program. Yep.
Do you mean to make your unconditional jump to else if instead of end if?
Oh, yes. I meant to change the label name to end if, not else if. Same thing. It is meant to go all the way to the end of the entire subroutine. Okay. So that should do it. Let's go ahead and test it. So we say make, and then we gdb main, and we put a breakpoint on line 7, run it all the way to line 7, and I just make it print the factorial of, oh, it's still using link. But it works. Isn't that mysterious? It is referring to link, everything is still referring to link, and it still works.
But it knows that, does it know that you're actually telling it to go to factorial inside of it?
Well, factorial is already known inside the executable. So in the executable, there is a label, factorial, because I exported factorial using .global inside that particular file. By default, it expects 5 as an integer, so it does pass 5 as a 32-bit integer, which is all factorial needs to use. Now, by default, it's also expecting a return value of integer type and have it stored in EAX, and that's why the whole thing still works, even though I did not make any changes to the main file.
This program can only do up to like factorial at 15, because after
Yeah,
15
it
crash. Well, not crash, but it will give it wrong.
Get a overflow.
yeah, I think isn't it 12 only? 13? Okay, so we got 1, 2, 3, 4, 5, 6. Yeah, 13 will be the last one, and then 14, it's gonna give you some unexpected value because we have overflown what we can represent using a 32-bit number. Now, whether it's signed or unsigned really does not matter in this case.
Second question.
Yep.
How would you fix that so that you could do, or can you?
To do more than 32-bit,
Well, just to be able to do numbers larger than.
you will have to use 64-bit numbers.
Okay.
Yep.
So you'd have to pull whatever's in EEX back in.
Right, but before we do anything else, we have to figure out what register combination is used to represent a 64-bit number. So now you have to kind of do some investigation to find out how the compiler represents 64-bit numbers. There are easy ways to do that. So basically what you do is you write a subroutine in C that returns a 64-bit number and make it a very unique combination, and then you call that in assembly. So when that subroutine returns into assembly code, you stop and you look at all the registers and see how the registers are being used. So that's a quick and easy way to kind of poke GCC and find out how it represents the 64-bit numbers. But once you understand how to pass this 64-bit numbers back as a return value, then we can go ahead and change the program to make use of 64-bit numbers. So are there any questions about this code at this point? Yep.
So in my code, I didn't actually use a call factorial. I used a jump back to this factorial and did my compare at the end. Other than not mirroring the C logic, is there any major problems with that? Because I know it doesn't mirror the C logic well, but it's still, I could put any number other than 0, and then I realized while you were explaining that if I put 0, it would have bombed out. But any other number, any positive number was working just fine, and I never used call factorial.
You are missing the experience of using recursion because your program is actually using a loop and it's not recursive. And because of the nature, you're jumping back to Factorial as a label, you're probably not pushing EBP and going through all the entry code either, because that would have broken your loop as well.
I used that before the loop.
Oh, so you're just making it into a loop.
Basically, it's just...
Yeah, so that means in the exam when it gives you a problem that has to be recursive, then it will be a new challenge to you.
Okay.
Whereas to the rest of the class, it's like, oh, okay.
But it seems like the only main difference, instead of doing a jump, I just would write call factorial and it would do the same thing basically in my code. I think.
With certain types of code, you cannot easily do it non-recursively. Like when you want to figure out Fibonacci numbers, that is not easy to do with a loop, but it is much easier to do it in using a recursion. Yeah.
So, I thought because the C code said to the factorial, I had thought it was a sign.
No, it was still come up with the same answer. It will still be right. The only time my code will work differently from code that uses unsigned numbers is when I try to figure out the factorial of -2.
Right.
In my code, it would just come back with a 1, but if you use unsigned interpretation in your code, it will just go through a lot of stuff and come up with some answer.
So is it a big mistake if I check for negative numbers?
You don't have to check for negative. I'm not going to dock any points.
Is it a big mistake you can do?
It is not a mistake, because, well, I'm not going to consider
that. I return the same number.
Yeah, I'm not going to consider that as a mistake, but it is definitely not consistent with the original C code. Yep.
So, just using the unsigned logic in this case on top of it.
You're not going to lose any points, but yet it is not the correct answer either. There are several things about homework assignments. One is how many points am I getting for my submission, okay, which is obviously important. I'm not saying that it is not important. But there's another thing about homework assignment is, especially for stuff like this, is do you know what is the code that its compiler will generate for this type of C code? That is a more important question to me. Okay, is what is not the end result? It is what is the compiler going to generate? What is the code that is underlying the C code in this particular case? So that's the other aspect of homework assignment is you go through that exercise, you learn basically how the compiler works and what kind of code is actually generated in the back end. And so you just kind of have to understand that there are two aspects of homework assignments. There's the point issue, and then there's also did you do it the right way so that you learn what you're supposed to learn from the homework assignments. Are there any other questions about this particular homework assignment? Questions? Okay. So if there are no questions about this homework assignment, I'm going to make a new folder here. and I'll just call that linked list. And then the first thing I'm going to do is to create a struct header file. So I'm going to just call that node.h. Okay. Now you don't have to take have taken the data structure class. I'm going to tell you guys exactly how a linked list works. It's basically one of the simplest data structure that you can do in C and C++. So it's not going to be that big of a deal. So I'm going to do a count if ndef node underscore h define node underscore h, and then here I will have I will define the struct called uppercase node, and if here, and I'll just give it something like struct node next. So this pointer points to the next node in the linked list, and then I will have one thing to store the value of this particular node. So for those of you who have not taken C++, the object the data structure class, okay, you just have to look at this as a structure definition. Okay. Are there any questions about this particular structure definition itself? What is a node? A node is basically one thing in a linked list. It's an item in the linked list. So the way a linked list works, this is my 1 minute explanation of one data structure, is you have a pointer pointing to a node. But a node has two things. It has a value. Let's say this one has a value of 1, and it has a pointer to point to the next one. And let's say this one has a value of 4. It has a link. It has a pointer to point to the next one, like this one. So eventually you get to the last item, and then the last item can identify that I do not have a next item by having this thing to point to a null value, which is basically just a 0. Yep. It's not doing a single thing. It is a pointer to a structure. That's all that it means. It's not doing a single thing. Looking at the data structure itself, looking at the definition of a struct does not tell you what it is supposed to do. But the code that I will give you next to this is going to tell you what it is going to do. Yes?
Are we going to create another object to have the contain the head pointer and some other data pointing to the first node, or just strictly from nodes?
The beginning of the entire list is going to be of a type of a pointer to a struct node, because it has to point to the first one. So it is a pointer to a struct node itself. So are there any questions about just the data definition itself, or the type definition itself? Questions? Okay. So now we move on, and we'll start to have subroutines to make use of this. Okay. So the first subroutine. Okay. So here we have another. We have main program including node.h to make use of the definition of the structure, and then in here I'm going to do some subroutine definition in C itself. Okay. So the first one that I'm going to make is called struct node make node, and in make node I can give it a particular value. Let's say v, and what this has to do is the following. It has a local variable that has the same type as a pointer to a struct node. So I'm just going to call this ptr. The first thing it has to do is to perform the allocation. So this is equivalent to a new in C++, but in plain C we just called it malloc. So in this case it is a malloc of a pointer. So we have to do a cast here, malloc size of struct node. So, okay. So let me explain what this particular line is doing. This line is basically starting with size of struct node. Size of struct node is not an actual operation. The compiler understands the structure, and it understands what is the size of that particular structure. So size of struct node is just going to return the number of bytes of one of those particular structures. That is used as a parameter to malloc. Malloc is not a subroutine you have to write. It is supplied by the C compiler or the C library. So what you have to do is to call it and tell it how many bytes you want to allocate. It returns a null pointer. and a null, not a null pointer, excuse me, it returns a void pointer because that's the type of malloc. A void pointer cannot be assigned to PTR because it is not the right type. So that's what the type casting is for, is casting a void pointer into the type that we want. Okay, so that's basically what this line looks like in C. And I'll do this in C++ too. Okay, not C++. I'll do this in assembly just to give you an idea of how to translate a C code into assembly code. The rest of this is really just to initialize the node that I have just made using the malloc call here. So I would make the value part the same as v, which is my parameter, and then the p next one, which is a pointer to the next node, is just going to be null. And if you prefer, a 0 is the same thing as a null. Are there any questions about this particular subroutine from the perspective of just being a C/C++ subroutine? Question? Okay. So the first thing I want to do is to implement this in assembly, and to do that in assembly, the first thing I need to do is to create a program that can print out the displacement to each individual member inside the structure, kind of like what we did last time, the tedious thing, with that program. So that's what we'll do next, is to define a program called node include file generator, and that will include node.h. And the only purpose of this particular program is to print out the displacement of different members from the beginning of the node to the member itself. So we'll do exactly the same thing as last time, and this time I'm just going to go through this real fast. So we'll use printf, and then we'll just say printf %u for unsigned integer. The first one is going to be node underscore PTR. The order is not even important. And then we'll say cast it to a void pointer, and this would be the address of n.ptr minus the address of n itself. And then from this, I can just copy and paste it just once. It's not PTR, it's called P next. The other one is value. And then the last one is going to be the size of a node. So I'm going to say node size. So that one is not going to be computed. It is just referring to the size of a struct node. That. Okay, are there any questions about this particular program? It's doing basically the same thing as the other program that we did last time. All it's going to do is to print out the displacement in number of bytes of any member from the beginning of a node. So we're going to run this program first just to make sure that it does work. And it's not going to work because I forgot to do a pound include of stdio, standard io.h. So gcc-o node include generation, node include generation.c, and then we can just run this program, and the output looks like that. Are there any questions about this part? Anything too exciting right now? No?
No, I was just wondering if you could bring back up the node in gen.
Oh. Yeah, I'm going to give you the file. This is creating a the seed tar file that you will need. So I'm going to give you everything that I do here. Okay. All right. So the next thing we need to do is to copy the make file over here. Oops. Where did I put it? Oh, I think it's in cisp310. Make file. Put it here. And then we'll change the make file to reflect what we're doing here. It's really about the same as what we did last time, except the names are modified because of the use of the node instead of a struct. And right now we don't have any assembly language file, so we can just get rid of that one. And that should be it. And we're going to make the main program do something. And it does do something here. But it doesn't have the main subroutine, so it's going to complain. I'm just going to give it a stub at this point that doesn't do anything. Okay. So the point is to make the makefile happy, and it would actually compile. And it's complaining about incompatible implicit declaration of built-in function on line 6. Oh, okay, so malloc depends on a particular header file. Okay, here's a quick question for those of you who use Linux for other things. How do I find out what is the include file that I need in order to use malloc correctly?
Go to system calls table.
Nope. We man it. Yep, so standard lib, std lib. I mean, you cannot possibly think that I can remember all of these things. I mean, if it's something I can look up in 5 seconds, I'm not going to remember it.
What you're trying to say is we shouldn't either.
Exactly.
Making sure I am.
Your mental capacity is so much, okay? So you can either use the capacity for memorizing something, or you can use it to understand something so you can apply some knowledge later on. So
Unless you have eidetic memory.
Unless you are John von Neumann, who has both, who has photographic memory and the intellectual capacity to do all kinds of thinking. Yeah, but individuals like that don't come along too often. All right, it's still complaining about control reaches end of non-void function without a return, but I thought I did a return 0 at the end.
Calling the main function.
Oh, it's complaining about this one. Okay, we'll just return PDR then. There we go. Make. It's still.
Main.c.
Hmm?
The main.c is the one that's
In function made node, incompatible types when returning type struct node. Oh, okay.
Yeah.
I'm returning an entire node. I should return a pointer to a node. Okay, thank you. Okay, but this does show you one point. You can return an entire structure in plain C. Okay, we don't have enough time to talk about how to return an entire structure, so we'll just kind of not talk about that one. But returning a pointer is easy. How do we return a pointer? Put it into EAX. Okay, anything that basically fits into 32-bit, we put it into EAX as the return value. Okay, so this way, I think the makefile is happy at this point. Excellent. Okay. So the next thing we want to do is to write the subroutine in C, in assembly. Instead of writing it in C, this subroutine here, we're going to write it in assembly, and basically say, just go through the process once to show you guys, how to do it in assembly. So here, I'm going to copy and paste this part just to keep the prototype, and then the rest, I'm going to use #if0 and #endif to quote-unquote comment it out. Now, this way of commenting out something is better than using the /* and */. The reason why this is slightly better is because this can nest. Okay, you can have nested #ifs to rule out to basically comment out stuff. Whereas if you use /* and */, it is not nestable. Because whatever you do inside, it's the first time it sees an */ it's going to close all the commenting, and it's not going to be. It cannot nest. This can nest. All right. So I'm going to save it, and then we'll go ahead and look at the assembly's implementation. And to do that, I'm going to split the screen so we can keep an eye on the C code while we work on the assembly code. And the convention that I use, when I do something like this, is the assembly file is going to have the same file. It's going to have the same name as the subroutine that I'm implementing. So this way I can look at the source file name and know that which subroutine I'm implementing. And this also kind of implies one thing. I'm only implementing one subroutine per file. Okay. So I use .global to export the name, make node, because otherwise the linker would not know that this object file is providing that particular symbolic name. All right. And then we'll go ahead and use the label definitions from before. OEBP is 0, return address is OEBP plus 4, and then we have the parameter, which is v here, which is return address plus 4. We have a local variable PTR here, so let's keep the same meaning as the C code. So PTR is going to be OEBP minus 4 because it is a local variable. It is on the negative side of OEBP. So at this point, I'm ready to go to define the subroutine. Make node is defined as follows: push L EBP, move L ESP to EBP. And then at the end of the subroutine, I will do exactly the opposite to restore the stack pointer and also the old frame pointer. And then I do the return. After I take a snapshot of the stack pointer to become the frame pointer, it is time to do some additional allocation for my local variable PTR. So this is where I do the additional add instruction to add the displacement of PTR to the stack pointer to basically allocate the stack space for my PTR local variable here. Are there any questions at this point?
I noticed that you moved where you had declarations to under.global and in the homework that you had it before.
Yeah, it doesn't really matter.
Okay.
You can put .global all the way to the end and that's basically scatter the label definitions all over the place. It really doesn't matter.
Okay.
Because the assembler, does not do things like C. It does not need to have to see something in order to use it. You can use it first and then define it later, so it doesn't matter.
Okay.
Yeah.
So, similar, but do we have to define the variables like old EBP and return address before the .global?
No. Yeah. Those you can move them around. You can even you can sprinkle them into the actual code and it will still work just fine. As long as you only have one definition, it will still be fine.
Skittles?
Yeah, Skittles. Yep.
I'm hungry.
Sprinkle. Okay, so now we have the stack all set up and we can now go ahead and implement the subroutine. The first one is this one here. Oh, we don't have anything that will tell us the size of a node nor the displacement to each individual member inside a node. What should I do?
Use that other program.
Yep, include the output of the other program. So I'm going to put here and say include, but I cannot include a .h file because it contains the syntax that only a C compiler understands. So in this one, I need to include node.inc. Okay. But once I have that file included, I would have certain labels that can tell me how many bytes I need to allocate when I call malloc. So what should I push here before I call malloc? $, and then what? Node size, exactly. I push the number of bytes that I'm supposed to allocate using malloc. I call malloc. When it comes back, I'm going to balance the stack because those 4 bytes on the stack I don't need anymore. But now, what is in EAX at this point? A pointer to a chunk of memory that I have just allocated, right? So my job is to store that into my local variable PTR. If I want to do things exactly the same as the C code, that's what I need to do. Okay. So that means I just need to copy the return value from malloc, which is in EAX already, into PTR, which is my local variable, to store a pointer to a struct node. Do we have any questions up to this point? questions? Okay. So the next step, whoa, stop. Okay. What about that typecast thing, of turning a void pointer into a struct node pointer? There's no type in assembly, so there's nothing to do. A pointer is a pointer. That's all. Okay. So that's why there's no typecasting here in order to finish this particular step. The next step is to go to the value member of the struct node that PTR points to and change that to V. Okay. Well, that's really a long way to do it because PTR is already in a particular register. Which register has the same value as PTR itself as a local variable?
ESP? Yes.
ESP? No. EAX. I just copied EAX into PTR. So EAX is still a pointer pointing to that chunk of memory, the beginning of the chunk of memory that I just allocated, which is the beginning of the entire structure. Okay. I want to copy B, which is my parameter, to a particular member of a structure pointed to by EAX. Okay, forget about PTR because it is already in EAX at this point. So how can I do that? Okay, so ideally speaking, what I really want to do is something like this. I want to copy V, which is passed to me as a parameter, and whatever, all the parameters and local variables, I have to access it through this particular addressing mode. And I want to copy this to the member called value of a node, and the node is already pointed to by EAX. So ideally speaking, this is what I want to do. Using a single move instruction, I would like to do this, but I can't. Why can't I utilize this particular instruction, having this particular operand combination?
You can't have two operands.
You cannot have two memory operands. Okay. In this case, both operands are base operands, and so they are both memory operands, and I cannot do that. So in case of trying to do something like this and we cannot do it, how do we get around this problem? You can use an intermediate register, but there's another way to do it.
Stack.
Exactly. Since we're talking about a stack, let's do it using the stack. So to do this using the stack, I'm going to do it like this. I will push the thing that contains the value that I want to copy from, and then I'll pop it into the destination. That will do it. It is not any more efficient. In fact, it is less efficient compared to the use of an intermediate register, but it just looks cool. But what you guys really should do is to understand why it is getting the job done. Okay, you push it on the stack and then you pop it, which is basically the same thing as a move instruction, except no register is involved in the process. I'm not using any intermediate register to get this done, which is the nice thing about this combination of instruction. Okay, what about the next one? Yep, go ahead.
You're not really using any new memory. You're not really using any new memory, so to speak. You're not like taking up a space.
You use stack.
You're reusing the space.
Yeah, I allocate and use 4 bytes, and then I deallocate those 4 bytes right away. In other words, the effect is not cumulative. I'm not chewing up memory, slowly. I'm just using it, and then I deallocate. What I am chewing up or wasting is processing time, because I'm doing additional memory access that I could have prevented using, another register. Okay. The next one I can't do with a single instruction because the next one just needs to copy a constant of 0 to the destination. So this one I can definitely do with just one single move instruction, moving a 0 into node underscore PTR, P next, of relative to where EAX points to. And I'm almost done. I need to return PTR at this point. In other words, technically speaking, I need to copy PTR to EAX. Do I have to do that? No. Nope, they're already the same. So I'm pretty much done already. This also means that PTR as a local variable is not exactly needed when I implement this in assembly, because I can keep using EAX throughout the entire subroutine, and there's no need to use PTR as a local variable. It's just because this subroutine is short and it's simple. But if I have additional calculations and whatnot, then I might need to use a local variable for that purpose. Yep.
Is calling malloc sort of like the new command in C?
Yeah, it is the same thing as a new operator in C++, except it doesn't automatically engage the constructor. So it's very low level. All you're doing is you're asking for the heap manager and say, give me a chunk of memory of this size, and it returns a pointer to that chunk of memory, and that's all it does.
That's why you use the when you define the malloc, you use the size of. Get an empty array of like the size you wanted. Whenever it was empty, right? Then when you use the size of, then you have an empty array.
Size of?
When you use size of there in the other one.
You can use size of you can apply that to anything. You can use a size of an integer if you want.
Yeah, but that's because we have to give it like a size of array or something. That's fine. Like you want a new one, new variable or something.
No, size of just said it will just tell you what is the size of something in number of bytes.
Like struct node, malloc size of struct node.
Yeah.
So that one is creating the malloc, creating what?
It is calling the heap manager, and it comes back with a pointer pointing to a chunk of memory that is just allocated of that size.
Of that size. Yeah.
I have a question. So you can compile this assembly file with
Well, let's give it a try.
With make file.
Yep.
But you can compile with assembly, like just assembly file.
That is correct. It has to do with, it has to go through the preprocessor. And AS does not know how to pass the source file through the preprocessor first.
And it doesn't know about malloc.
Oh, malloc is not a problem, because the linker has to do with malloc, not the assembler. The assembler only has to say, oh, you're calling malloc and it's not defined here. I'm going to put the unresolved reference in the object file itself to be resolved by the linker. So ultimately, it is the linker, LD, that has to do with it. But GCC, basically automatically, call the linker, but it will also supply the library. In this case, it will supply the standard C.
Yeah, but
as
how
a,
do you do it if you just want to compile with assembly file?
well, let's look up, AS and preprocessor. Doesn't seem to have a way to go through the preprocessor, so this may not be easy to do. No CPP. Oh, okay, so it does have that option. Oh, but that's only for MIPS architecture, so it's probably not. There's no easy option to do it. Okay, so we'll go through mains, and it's not working just yet because I have to modify the makefile to include the assembly source code here. So this is what make node, and it's complaining about the same thing as last time. It is complaining that node.inc is not in that file. So we'll have to trigger the creation of that first. I'm going to generate the first one by hand first, and then after that, everything should be okay. There we go. The program is not going to be able, we cannot test it. Well, I suppose we can test it, but we have to modify main a little bit to test it. Okay. So the question is, how do we test this particular subroutine when I don't have anything else that make use of the subroutine? So what we'll do is we'll just go ahead and allocate a local variable pointer. Let's just call this PTR, and then we'll say PTR is going to store the result of make node, and we'll just make a node and store the value of 123. And then we'll go ahead and run this. And then inside the debugger, we'll be able to examine the pointer and what it points to. Are there any questions that I can answer? You know, it's the second time I'm asking that question. No? Okay. All right, so we'll do another make here, and then we'll variable PTR is set but not used, but that's okay because that was actually the intention of the program. I do not want the compiler to optimize this out. Okay, so we'll go ahead and do a gdb main, list the program, and put a breakpoint on line 21. You know, right after PTR gets a value, run the program, and then I'll just print PTR, and it does optimize it out. Okay, so I have to make use of PTR so it doesn't optimize the code out.
Like printf.
Or I can specify, I thought -0. Okay, let's specify -0 to specify that we are not optimizing anything, and see if the compiler is still annoying and touch. Let's see, make. It's still gonna optimize it out. Okay. How smart do you think is the compiler? In other words, do you think it will figure that this is useless? Maybe? Okay, let's check out the compiler. Oh, it is not that smart. It does not complain this time. It did not optimize that code out. Great, Tag, you just outsmarted a compiler.
Good job. How does that make you feel?
I feel that I'm smarter than a compiler.
Isn't there a different optimization thing?
Yeah, well, you know, I use -O0 to try to turn off every single possible optimization, but the compiler is still smart enough to figure out and say, hey, you're not making use of this variable. Let's not even do anything. Yep.
What is optimization? What is optimization?
Optimization means doing as little as possible and still do what your program is supposed to do. In the case of people, we call them lazy, but still getting the work done.
Okay.
Yeah. Yeah. All right. So we just set a breakpoint here. We run the program up to the breakpoint, and here we're gonna print PTR, and it gives me a pointer, which is not very useful. But since we're in GDB, and GDB is smart, okay, because we included all the debug information. So what we can do here is to say, don't show me PTR, show me what it points to. And here we have, you know, P next being null, and value is 123. The program worked. Okay, the subroutine make node routine assembly actually worked. Yep.
Will we work under C syntax where we just say print pointer arrow value? Will that work? Or no?
It will work too. Yeah, it understands C syntax. GDB understands C also. So if you say PTR points to value, same thing, it will do the right thing. If you tell it to print the P next, it will print null. Okay, so it does, it does understand the syntax as well as the meaning in C operators and also the members of a structure. So do we have any questions about this really kind of simple subroutine? No? Okay. So what we're going to do next is we'll make this program a little bit more complicated. Okay? So the way we make this program slightly more complicated is like this. So we go back to main here, and what I'm going to do is to say, all right, so let's do this in a loop. Okay, so I'm going to say while scanf %, what is that? %u for unsigned integer, so that's what I'm going to do here. So it's going to read from standard in, or try to read from standard in an unsigned integer, and then put it into a local variable. I'm just call that u also here. So I'm going to declare a unsigned int u. And what I do want to show you is what scanf is supposed to return here. Okay, so this is the documentation of scanf, and scanf is supposed to return a value. What it returns is an integer, and if you look at the return value, which is scanf reads input from the standard input file. And it's going to return a value specified down here. Okay, I just cheated. I looked for the word return. Okay, so return value. These functions return the number of input items successfully read and assigned, which can be fewer than what is provided for, or even 0 in case of matching failure. The value EOF is returned if the end of input is reached before the unsuccessful conversion or a matching failure occurs. So we have to look for EOF, which is a negative value, or 0 in this case, because I'm only attempting to read one thing. So if it is successful, it's going to read back 1. If it is not successful, for whatever reason, it's going to be not 1. Okay, so I'm just reading 1 or not 1. So inside the program here, what I'm going to do is to compare the return value of scanf, and just say that if it is 1, we'll keep going. If it is not 1, I'm going to get out of this loop here. So inside the loop here, it is going to have the value already stored in my local variable u. So the next question is, what am I going to do with that, right? Okay. The first thing I'm going to do is to use ptr gets make node, but this time I'm not going to make a node to store the value 123. This time I'm going to make it store the value that I have just read, which is stored in local variable u. Okay? But remember what I want to do with this program. I want to store these values in a linked list, and I want that list to be sorted. So the next thing we need to do is to write a subroutine to traverse a given linked list and find out at what point I should insert that particular value or insert that particular node. Okay, I'll give you an example. Even though this is not a data structure class, this is something that we can cover in about 5 minutes. So, okay, let's say that we have a linked list like this already created. If I have a new value coming in, let's say it's 2, okay, what should I do? I follow this link, I follow this pointer here and say, okay, we don't have an empty list for sure because it is pointing to something. It's pointing to this node here. I go to this node and say, what is your value? I have a value of 1. Okay. Do you think 2 should be here taking the place of this guy, or do you think 2 should be somewhere down the line? It should be somewhere down the line. Okay. So I follow this link here, and I go to the second node on this list here. The second node said, I have a value of 4. And then I look at the value that I'm supposed to insert into the list and go like, oops, I got 1 step too far. So when you are 1 step too far, then you have to somehow keep the pointer to this pointer here and be able to say, you know what, you should not point to here anymore. I want you to point to here now. What is here? This is the new node with a value of 2, and then this guy will now point here. So this is the first step to do to make this pointer, instead of pointing here, to point here. And then this new node is going to have its own pointer pointing to the node that I'm already at that point. Is that making any sense?
Yep. You complain that it's not next number is not 3. Point something else then? Wouldn't it complain like, hey, the next number is not 3, and then it would make a new one for itself and 3, and then it would point to 4?
No, I just want to maintain a list that is sorted. That's all I want to do. And I don't want to store duplicate items. So if 2 is already here, I'm just going to say, okay, we don't have to do a single thing about that. Okay? So let's go ahead and write a subroutine to do this part of the logic. We start with the beginning of the list, and then we traverse the list node by node until we get to the point where we say, oops, it's too late. Let's back up 1 little step and change that to point to this new node, or create a new node at that point. Yep.
So no duplicates, huh?
Say again?
No duplicates. If you have another two.
Another,
No duplicates.
no duplicates, right? So if we have a value of 2 already, I'm not going to create another node to add to the list. Okay. All right. So I'm going to take out this code here, and I'm just going to call a particular subroutine. I'll just call this insert into list. Okay. And in order to have a list here, I'm going to change the name of PTR and say this is my list. But instead of passing list by value, I'm going to use the address of list to pass to insert into list. Okay. So we'll take a look at why that is necessary. Why is it so complicated? Why do we have to do this? And then we also have to specify the value that we are trying to add to the list. In this case, it is stored in variable u. Insert into list. It takes 2 parameters. What is the type of the first parameter? Just knowing. Okay, excuse me. Do you guys have a question? Okay.
I haven't said one thing at all.
Oh, okay.
I literally haven't said one thing.
All right. So, what is the type of list in this case?
No.
It's a struct node. It's related to a struct node, but it's not a struct node. What is list itself? It's a pointer to a struct node. And what did I do in order to pass it as a parameter? I took the address of list. So what is the address of a pointer to a struct node? It is a pointer to a struct node. It's a pointer, it's a struct node asterisk asterisk. Or, if I prefer, and I can still call it list. But it is really not a list, it is a pointer to a list. Okay, how many people have dealt with pointers to a pointer? Okay, so is it any different from a regular pointer?
Just C. Well, like you said, it's just another address.
Okay, so let's say this thing represents a struct node. Okay, a struct node has 2 items. It has a p next, it has a value. Is that okay? What is a pointer to a struct node? A pointer to a struct node, as the name implies, just points to a struct node. So this one is a struct node pointer. What is a pointer to a struct node? Is that okay?
It's just like with ints. A pointer to an int is just an int pointer, and a pointer to an int is just an int pointer with 2 addresses.
Well, a pointer is just, you're storing the address of whatever it points to. So in this case, we start with a struct node, which is the data structure that has 2 members. A struct node pointer points to a struct node, which means it is storing the address of a struct node. A struct node, a pointer to a struct node is the address of a struct node pointer. I mean, there's really no easier way to explain this, except each one is a pointer. It's a way to find the next item. Okay. But there is a reason why we need this. Okay, the first thing we also have to do is to initialize list. Because if a list is empty, it is pointing to a null value to indicate, okay, this list has nothing in it. Okay. So knowing that, I'm just kind of inconsistent here with the use of integers and whatnot. So I'm going to change, I have to change one of these. I'm going to keep using unsigned here. So this is unsigned int u. Okay. I want to make this recursive. So to make this recursive means that I have to decide when to stop the recursion and when to continue the recursion and say, I don't know what to do with this, but I bet you the next guy knows. Okay? That's basically the whole point of recursion is, if I know what to do with this, I'll do it and I'll return. If I don't know what to do with this, I'm going to pass this along to the next person. Let that person deal with it, and when I get the result back from that next person, I'll just come back with that answer. Okay. So we'll look for a few cases where I know what to do at this point. Okay? The first one is if plist is null, then I can stop the recursion. Because if plist is pointing to a pointer that is null, that means the list itself is empty. If the list is empty, I know exactly where to insert this additional node, don't I? Okay. So that means in this case, I just have to call the function that we have defined a little bit earlier, make node, and we basically say plist, or whatever plist points to, which is a pointer to a struct node, is going to get the value of whatever make node returns in this case, and I'm just going to pass v along u instead of v. I'm changing the type. Okay, and that basically stops the recursion. Yep.
It could be either empty or it could be at the tail end of it, right?
Exactly, but when you're dealing with recursion, you don't need to know. It is the same case whether you are at the beginning of the list and it is an empty list, as opposed to you are the last item of the list and I'm inserting 9 here. Okay, if I'm inserting 9, then eventually the recursion will get to this point where plist is going to point to a value that is null. Now, plist itself is not null. It is what it points to that can be null. Okay, so that you have to be careful with that. But there's another case where I can also end the recursion. The other case when I can end the recursion is I look at plist as a pointer. If that thing points to something that has a value that is the same as my parameter u here, I'm also done. There's nothing to do here. Is that making any sense? Because I said earlier that we are not storing duplicate values. So if some node in the list is already storing the value that I want to store right now, there's nothing I need to do. Okay, I can stop. There's also another case where we can stop. The other case where we can stop is when we realize that we have gone past the point. In other words, if I want the list to be sorted in an increasing order, that means if I'm seeing a value that is larger than the value that I'm supposed to insert, I can stop also. Okay. So in this case, if value is greater than what I'm supposed to store, I can stop also. But in this case, when I stop, I cannot just say, oh, there's nothing to do, because I do have something to do. Because I have to go through this process here. Whoever points to me as a node needs to point to a new node that I'm creating, and the new node needs to point to the node that was pointed to before I the pointer that was here before. Is that okay? Okay. So I'm gonna have to go through that process.
Value, where did value come from? Where did the value come from?
Value is one of the members of a struct node. It's one of the two members.
Oh, it's struct node?
Yeah.
Okay.
Okay.
You need to change
So,
pointer.
sorry?
Pointer to plist, you need to change pointer.
Okay, I need a particular pointer here as a temporary pointer. So that thing is going to store whatever plist points to. Yes, okay. I'm just double checking mentally, whether I'm doing this correctly or not.
Plist equals.
Say again?
Plist equals plist pointer to next.
Plist is going to get, that's the last part. Yep. So the next thing I have to do is to use a make node, u, and then this thing is going to point back to, oh, okay, I got you. Yep, I need that part here. And then the new node the P next of this new node would now be TMP, so it points back to that one. Okay, so let's take a look. Let's take a quick look at these 3 lines and see how it relates to this picture here. I'm going to erase all of this stuff here and then show you guys exactly which line is doing what to this linked list. The first line, which is temp gets in parentheses asterisk P list and then outside parentheses point to P next, is basically just saying TMP is another pointer. I'm taking this pointer here and then say, oh, okay, let's see what the next number is of this structure, and we'll make PTR point to the same place. That's the first instruction. The second instruction is to create a new node. In this case, it will create a new node with a value of 2, but the pointer is pointing to null, and by default, I make node. That's the second instruction, or second line of the code. The third line of the code is to say, there are 2 things that this is actually doing. The other thing this is doing is to change this pointer to point here instead of here. The third thing we're doing is to say that the next of this new node is going to point to whatever TMP points to, which is the actual next node.
Wait, then what happened to the pointer pointing to the 4?
It's changed from here to here. In the second step.
So did we get rid of it? Like
Nope.
the 4?
Nope, because
The temp should point to 8, but
oh, you're right. Okay. So this thing has to point back to here. So that means the temp should point to this guy and not the one to the next. You're right. Okay. I think that should do it. Okay, temp points to the current node, and then we change whoever is pointing to the current node to point to a new node, and then we make the new node to point to the current node, so that will finish the chain. Yep.
Do we need to deallocate temp when we're using assembly, or does it take care of it itself?
Well, temp is a pointer, so it is okay for temp to go away because it's not going to do anything. It's not going to delete what temp points to. It's just deleting the pointing itself. So the extra pointer is pointed here. We're just removing this. But it is still, this node is still pointed to by this pointer, by the data structure. All right, we are almost running out of time. Okay, I want to test this. Okay, do you think I can test this at this point? Without anything to print out anything? Yep.
You can do whatever you want, doesn't mean it's gonna work.
Exactly. That's a very good point. Don't we all know that part now, right? Incompatible implicit declaration of built-in function by default. Man scanf. It's instead IO. Okay, let's do GDB because the program has no output. Without GDB, I cannot see a single thing. So let's run it through GDB list, and we'll put a breakpoint on line 44. Oops. That's 45 lines. Okay, all right. Run the program. Now it's reading the numbers. Okay, so I can give you numbers like 6, 4, 5, and that's it. To end the program, I can give it something that is not a number, and it should end automatically. So now I'm at return 0. So the question is, did I construct the list correctly so that it will have items? The first one should have a value of 4, the second one should have a value of 5, and then the last one has a value of 6. Okay, so this is the moment of truth. Did it work correctly? Print whatever list points to. Okay, it's a 4, so that's a good sign. And the pointer pointing to the next one is not null, so that's also a good sign. So the next thing we have to do is to say, okay, but what is the next item of this one? 6. Ah, and a null. Okay, so it did not work correctly. Okay. Let's debug it. Okay, so the numbers are 6, 4, and 5. It did store the 4 correctly. It did not store the 5 correctly, so the last number was not stored correctly. So that tells me that when it comes in, the list, which is a pointer, created an item called 6, and that was done correctly, because otherwise we would not be seeing 6 being done correctly. When the 5 comes in, when the 4 comes in, it has to do it correctly too, because otherwise we wouldn't be seeing the 4 here. So list points to a node that has a value of 4, and that points to another node that has a value of 6, and that ends the list. When 5 comes in, for whatever reason, it is not handling that case correctly. But that really is a new case, okay? That is a new case, because when 5 comes in, it will first compare to 4. It knows it's not, oh, I did not do the recursion, did I?
No.
No.
Sorry for next time.
Okay. Because I did say that this is a recursive subroutine, and yet
Right now it is.
there's no recursion. All right. So the recursion goes like this. It is the last case. I caught all of the base cases, except I forgot to do the last one, which is, what if all the base cases did not catch it? Nothing to do. Okay. All right, so here's the recursion. The recursion goes like this. We are just saying insert into list. But where is my list now? I'm just using extra parentheses to make this really clear. Okay, plist is the current node. Okay, plist, or whatever plist points to the current node. Okay, which has a next field. Okay, that next field, becomes a pointer to the next node. So I need to pass it to the next invocation. Except I don't expect a pointer to a struct node. I expect a pointer to a struct node. That's why I need to take the address of that thing. Okay? And it's passing along u because that's actually representing the value. Yes?
You're passing the reference of the pointer to a struct node.
In this case, okay, what I'm passing.
I'm sorry, you're passing the address of a pointer to a struct node. Because you're expecting a pointer to a pointer.
What I'm passing is this. This is what I'm passing. So I'm not passing this guy, I'm passing the address of this particular pointer, so that the next invocation, if it needs to, it can change this guy. Yep.
What is the case in the else the first else that is cases that if it's equal to the unit, then what?
Then there's nothing to do. It just ends because I have found the value. I can duplicate it. There's nothing to do for it. Okay. All right. So let's see if this works. GDB main. Put a breakpoint on line 48. Run the program. 645A. Print what is list pointing to, and then print what is the next node of list pointing to, and well, that's the beauty of a linked list, is we can keep stashing, the point to p next and keep going. So it does work now. I'm going to finish up this program and upload it. And can anyone guess what your job is for this particular homework assignment?
Do it assembly.
Not a binary search. You're going to implement the subroutine that I just finished debugging. So you don't have any debugging as far as the logic is concerned, but you do have to implement it in assembly.
I'm sorry, what you're doing now is sorting.
Yeah, I'm just doing a very simple sorting, but you have to implement the program using the structure. Okay. When we get to the lab, I can explain, a little more. Those of you who wanted to start it early.
When are they going to be due?
Maybe I'll find a guy.
the day of the final?
We have until the end of the semester. So our last homework will be due. But I think it is better to get it done before the final, because it is actually a way of studying for the final.
How about Tuesday at 2 o'clock? How about before the final? Tuesday, listen to this guy. How about before the final?
Before the final, sometime before the final.
How about the 2 minutes before the final?
One.
All right, 1.5 minutes. We'll compromise.
Compromise.
I think the final's in 2 weeks. Or
Is it the 19th for this class?
It's 21st.
21st?
21st. You're the last one. You are the last one.
it's not the 20th?
I just want to double check. Not that I don't trust you anymore. This is a Tuesday, Thursday class, and the class time starts at 7 p.m. It's the 20th.
20th? That's what I thought.
Yeah, the 20th, not the 21st.
So, for my little loop, am I going to get a 0 or get any partial credit on that one, out of curiosity?
I'll give you partial for that, for sure.
I got it to
Because
work,
Because you spent time, you understood
And
how
I
to
did
get to
the
the
push and the pops,
parameters.
and I did the allocating the EVP, or the EVP, and I did that, and I understood what that did. And now I really understand it because we went over it.
Well, that
So.
is the most important part because but I cannot give you full credit because
No, I expect
compared
a
to
few
what
down. Plus, I did my compare at the end. That's how come I did my conditional jump, because I did my compare after I did the multiplication, and I used an intermediate
in
register. I
letter-
used
in-
EVX instead of doing it all on the stack. So.
In letter grade, I would call this between the B minus and the C plus. So I would just assign the points accordingly.
I just hate seeing that big 0.
No,
it compiles,
it's not
it
going
runs,
to be.
it works.
No,
so.
it's not a big 0. Big 0 is reserved for people who turn in programs that do not assemble.
Yeah, mine
do
works.
not link
It works.
gives
And
me
in fact
infinite
yours.
loops.
No.
Yeah.
But mine won't also work if you put a 0.
Yours
because
does not qualify
I didn't,
for a 0.
If mine went to 0, I didn't put a 1 into EAX, so it returns. If you try and factor and you put in 0 as your parameter, my program will be like. I forgot to do that part. So.
Okay.
Yeah, and there was a couple things I did wrong, and I was like, I just could not get this damn thing to
Well,
work.
thank you for your confession.
Yeah, what are you gonna do? It's all about learning, anyways.
Yes, this homework's going to be Thursday, and the final is Tuesday after that.
Well, the final is on the 20th, and we are on the 8th right now. So if I make this due on the 19th, then you will still have a week and a half or something like that. So that's plenty of time. The problem with this is if you give you guys more time, then let's say making this due next Tuesday, is most people will procrastinate. Or they have better things to do like preparing for other exams and other assignments. So by the time they get started, they would have procrastinated everything that I talked about today. Yes, I know the YouTube is online, but even if you watch the YouTube again, it takes time for your brain to reconnect all the concepts that is already established at this point. So it is a good idea to get started early, but I understand that some people have other things to do. You have to prepare for other classes, other exams, and so on. And we are close to the end of the entire exam week, so some people will say, I have my calculus like the day before. I cannot work on assembly and programming class until then. So I can understand that.
I was trying to hit it up by Tuesday.
Yeah, I would do it as quickly, as early as possible, just because we have all the information at this point, and if you just kind of keep going at this point, it's not going to be that much of a push to make it done.
So it's due the.
I'm going to make it due on the 19th.
Okay.
Because I don't want to make it due on the 20th because it's the purpose of the program is to help you guys kind of understand the concept and actually study for it.
We're going to mark this down if we're not using IMO. If we're not using IMO, if we're just using
No, I'm not going to.
Yeah, because I did the few things different. Like I used.
The main purpose of that assignment is the understanding of how the stack is organized, how to do the entry, how to do the entry code to make use of the frame pointer, and how to use the base addressing mode to get the parameter values on the side. So those are the main point of this particular homework assignment. The signed list of that, ideally speaking, if you just do that, is better.
So you don't care if we use like, was it the
conditional branch instruction? Instead of JNG, use
it's the equivalent of like the decrement operator? Or Because I use a decrement instead of
So
minus
Professor,
1.
when is this going to be due?
19th.
19th?
Yep.
Day before finals on Monday.
Yeah, the final is on the 20th. I'm gonna make this due on the 19th, just to make sure that people get it done before the final, as a way to prepare for the final. Wait, I just said too much. Forget about it. Retract.
I hate pointers, I'm just gonna be honest.
Huh?
I hate pointers.
You hate pointers?
Yeah, pointers to pointers to pointers.
Well.
Look, Araj had us do a project where we had a pointer to a pointer to a pointer.